The most important linear transformation, the most important change of units of measurements is conversion to standard units. Recall from data 8 that standard units answer the following question. How many SDs above the mean is your variable? Now, there's my variable, there's the mean, that's how far it is above the mean. How many SDs is that? Well, we have to look at that difference relative to an SD. This random variable, so you now have a function of capital X. This random variable is called X in standard units. Z can be positive if X is above its mean, if the value of X is above its mean, negative if the value is below its mean, 0 if capital X is at mean. Z is a linear transformation of X. Look at that. X is not being squared. Everything else is constant. That's a linear transformation. If you want to write it out in gory detail, in your slope-intercept form, there's your line. And this shows you, well, actually, the first form shows you easily that the expectation of your converted random variable is 0. And the second form shows you that the standard deviation of the converted random variable is 1. Because you're applying a linear transformation facts, the shift by mu x over sigma x doesn't affect anything. And so your standard deviation of z is 1 over sigma x times sigma x, and that's your 1. And while we're about it, what's the variance of z? Yeah, 1 squared, that's also 1. Well, we're on a roll here, so let's write another one. What is the expectation of z squared? Keep in mind that these three quantities are linked. This one, and this one. Any random variable, the variance is the expected square minus the square of the expectation. So 1 is equal to expectation of z squared minus the square of the expectation. And so, yep, the expectation of z squared is 1 as well. So if you have a random variable that has been converted to standard units, then its mean is 0, its SD is 1, its variance is 1, its expected square is 1. This is going to be extremely handy. And by Chebyshev implies that if you look at z, you look at how far off z is from its mean. Now its mean is 0, so that's how far off z is from its mean. And the chance that that is, say, bigger than or equal to 5 standard deviations, the standard deviation is 1, that is at most 1 in 25. If you have a variable that has been converted to standard units, then the bulk of the probability is going to be in the range minus 5 to 5. You'll have some outside, but not much at all. And finally, you should be able to go back and forth. X, if you have X, then that's how you go from X to Z. And if you have Z, then remember that Z measures how many SDs. So you are that many SDs above the mean. And I like to draw my two axes. That's my x scale and there's my z scale. So here I have mu x and then sorry, and the minute you've got 2 points on a scale, you know your entire scale. So that's mean plus or minus 1 standard deviation plus or minus 2 standard deviations, and that's my x scale. And when you go to the z scale, that becomes your 0 and that becomes your 1. And so then 1 standard deviation below, 2 standard deviations below, 2 standard deviations above. And what you do to get to here is that's the transformation to z. You take x minus mu x over sigma x. And what you do to get back, that's z. To get back to x, you do sigma z standard deviations above the mean. And this movement back and forth should become like breathing, because we're going to do a whole lot of conversions to standard units, especially when we work with normal distributions.